What we were trying to do is really quantitatively establish trade-offs between environmental variables and economic variables at the end of life. And in this case study, we were looking at energy recovery. We were talking about a coffee maker, which is a product that you now know very well. So basically, we'll just go through here as some of the previous literature, some of the holes that we established in the disassembly planning literature, the end-of-life strategy planning literature, and what we did. So we're actually being somewhat tutorial in this paper, recommending 6 steps that you can go through to model a product, model its end of life, the trade-offs, and then some of the methodology you might use. We won't talk about that here, how the trade-offs were established, the computational coding of this using genetic algorithms that Kareem really backed us up on in this case study. But nevertheless, it's described in the paper. Okay, we'll talk about sensitivity to situational variables. That was another point we wanted to bring out in this paper. So we're looking at multi-criteria decision-making under different situations. Under Aachen, Germany versus Ann Arbor, United States. What would you do different in these 2 case studies? Okay. So basically, 3 objectives. We want to develop a methodology that does not require you to enumerate all of the end-of-life possibilities. So just suppose that I have 12 disassembly steps for this coffee maker. So I can now disassemble this in a large variety of different disassembly sequences. I have to pick one of those. And now for each disassembly sequence and each part that's disassembled, I have to figure out the end-of-life fate. Am I going to recycle it? Am I going to reuse it? Am I going to dispose of it? All right? So now each product has 3 options associated with it. Now, with the remainder of the product, I can landfill it. I can continue to disassemble it. I can shred it for recycling. You can see that the number of options gets really large. I forget the actual number. It was something like 10 to the 19 or something like that in this case study. If you looked at just enumerating all of the options, okay, now you can get smart and whittle that down. But for the PCs that we're using, it would take way too long. Years and years and years to get an answer. Right? So in the disassembly planning literature, there are techniques that help you get that time down. But what we were talking about here is multi-criteria. Not just cost as a single dimension. What's the best thing to do from the environmental or the economic standpoint, but also from the environmental standpoint. So we basically had 2 axes to look at. So we had to be very clever about how to enumerate the best solutions. You don't want to look at all the solutions. You just want to look at what's called the Pareto set. For a given cost, what's the best I can do environmentally? And establish what's called the Pareto frontier. For a given cost, this is the best environmental performance, in this case energy recovery performance, that I can achieve. Okay, so this paper is about establishing those Pareto sets in a very computationally efficient way, using genetic algorithms. I won't say anything more about the method. You can read the paper if you're interested. Okay, but multi-criteria decision-making. Now doing it under multiple situations. All right, to take it one step further. Now we want to change the situational variables. We want to look at costs in Ann Arbor and costs in Ann Arbor and Aachen, excuse me. Okay, transportation distances change, labor costs change, the distances change, the infrastructure essentially changes. So you've got so many variables that situational analysis becomes quite difficult, especially when you're talking about now 2 different situations and all these different variables. Okay, so we're talking about using genetic algorithms to do this. And we also wanted to see in this investigation whether we could represent this information, all this complex information, in a simple way on a label. And you be the judge. I think it's not very intuitive. But once you see the label and understand it, it turns out after that 10 minutes of mental gymnastics, it actually becomes clear what it's saying. Right? So there's some training involved, but I wouldn't say what we came up with is necessarily intuitive. Right? But presenting the information becomes critical too. Okay, I won't say much about the previous literature. There's a ton of disassembly literature out there. Why are we different in this particular paper? Well, most of it looks at disassembly efficiency, using only metrics of cost. Right? So what's my target in terms of disassembly? What am I trying to get out? What's that little piece of gold in the disassembly? And how can I most cost effectively reach it? And there are a large number of clever strategies out there to do this. Most of it's economically focused, as it says here. Environmentally minded objectives are recognized, but they're not put on equal footing. It's cost that really drives most of that literature. People have looked at disassembly of the coffee maker. In fact, we've looked at it. There have been a number of case studies. But they haven't looked at the coffee maker under multiple situations. Okay? And under using both environmental and cost considerations on equal footing. Okay, like some of the data you're going to see here. Some sensitivity analysis has been done, but not in the way we're doing it, and I can't really say too much more about it. Pareto sets are becoming more recognized, the trade-offs in environmental design. There's an excellent paper. Uses a different method. They're not using genetic algorithms. They're using linear programming. In chemical engineering, it's related to BOD, effluent reduction, which is a problem that you can read and understand very well. It's a paper that is quite excellent, recognizing the trade-offs and how to decide among these trade-offs. But there isn't a lot of Pareto set analysis going on. Okay, so basically in this paper, we're trying to come up with a demonstrative case study. 6 steps we end up recommending here. Number 1, for this coffee maker, to define the situational variables. What's important to model? The labor costs certainly will be important. The transportation distances related to the transportation costs are important. The disassembly times are important. Whether you're going to consider reuse of parts. We didn't consider reuse for the coffee maker. We just couldn't conceive of a scenario where reuse was really going to be an option. So we didn't look at that here. We're just talking about recycling and landfill disposal. So define your variables, number 1. Number 2, define the product structure and the feasible set of disassembly sequences. And if you can consolidate disassembly sequences into clusters, then that would be a good thing to do because it will reduce the computational time. Even in a clever method, this still takes a while to do. Develop an environmental and economic assessment model. Right? You need a life cycle assessment model for the end-of-life scenarios. Right? What's the impact of transportation? What's the impact of landfill? Okay. We need an economic model for transportation. Disassembly. The disassembly times. Right? If I've got all these different options, how do I model how long it's going to take to disassemble the coffee maker? Because it's going to be related to how much I have to pay somebody to do it, and that's going to be related to my cost. So we need these models. So step 3 is establishing these models, and we've done a lot of this modeling in the class already. Then formulate your multi-objective optimization problem based on the models and metrics for product disassembly, the end-of-life economics, and environmental impact. In this case, our metric for environmental impact is energy recovery and only energy recovery. Certainly, we could have done more, but in the case study, even this one took about 2 years to do, just to get our arms around what's been done, what do we need to do, and what's the way we want to approach this. Okay, so this wasn't an easy thing to do. Calculate the optimal trade-off sets, okay, using the methodology, this multi-criteria optimization approach. That, by the way, had been developed in the literature already. The use of genetic algorithms for multi-criteria decision-making had been used already, been previously developed. And actually, there was quite a bit of code developed both here at the University of Michigan and elsewhere in the international academic community. We're just borrowing that and using it here because it works quite nicely. So use that, calculate the sensitivity analysis for these trade-off variables, and try to represent those results in a clean form. Okay, so 6 steps with some jargon that I've thrown in here. Right, I've talked about a disassembly sequence. Right, this is the order in which the part's going to be taken, or the product's going to be taken apart. Okay, and that matters. How far I take it apart and the order of the steps is going to lead to my time. And there was a whole master's thesis. This was Kumar's master's thesis, or secondary thesis in Aachen, Germany, at the Technical University of Aachen. He basically just modeled the disassembly of the coffee maker. So it took him some time just to do that. The end-of-life strategy. So this is the set of all end-of-life decisions, including the disassembly sequence, as we've just defined, the end-of-life fate for each removed component, and the residual. So if I only disassemble half of the coffee maker, what am I going to do with each disassembled part and now the residual. Am I just going to landfill that, or am I going to shred it and recycle what can be recycled from the fractional remainder? Situational variable, these are the important variables that define an influential aspect under the context under which that end-of-life strategy is being carried out. So the labor rate is an example here. Right? Labor rate is higher in Germany than it is here. The transportation distances, the infrastructure, etc. The laws are a situational variable. So the WEEE plays into the disassembly and remanufacture recycling of a coffee maker in Aachen, and it doesn't in the United States. So that's a situational variable, also the regulatory variable. The scenario is a set of all situational variables. So we've got the Aachen scenario and the Ann Arbor scenario in 2002 that we're analyzing here. Okay, so that's the jargon. These are our 6 steps to better end-of-life management, I guess. So it kind of sounds like a program of some type, right? But basically 6 steps here just in a graphical form. All right, defining the end-of-life scenarios, defining the product model, the evaluation model from economics and environment, the optimization problem, the Pareto sets, and then the representation. Okay, so these are the 6 steps which we underwent. These are our variables, the situational variables. Step 1, talking about recycling prices. We held those fixed from Ann Arbor and Aachen. They weren't very different, so we just set them to be equivalent. And they do change over time, so you have to recognize this was March 2002 recycling prices that we talked about. Transportation prices were represented as being the same, but the transportation distances were different. So the variable here shows up under infrastructure. Okay. Labor prices we talked about. The transportation method, we had the same here, small truck. The recycling and remanufacturing technology and efficiency was assumed to be the same. So we're just talking about recycling here. Energy recovery, and that was assumed to be the same in the US and Aachen, Germany. And I should say Ann Arbor and Aachen, Germany. The WEEE is in play in Aachen. We also looked at carbon taxes. I won't present those data here. And subsidies we could look at, different regulatory variables. Okay, so these are the things that we're going to vary. We're going to get these Pareto sets, and now we're going to change some situational variables, and then we're going to get a new Pareto set, and we're going to compare Pareto sets. So that's what we're doing. Okay, I won't, in the interest of time, say too much about how this is done. Again, I can't do it justice here anyway. But basically what we're talking about is looking at the disassembly of the coffee maker, trying to establish physical relationships and feasible disassembly sequences for the coffee maker. So you want to make a graph that looks like this. And Kumars and Kareem here and Aaron worked very hard to disassemble this coffee maker. They clustered components together into sub-assemblies to get the computational time down where it made sense to do so. But certain components you can take apart only after other ones have been taken apart. And that's the point, that there's only a set of disassembly sequences. You can represent this mathematically, by the way, right? And that's what's done, because eventually what you're going to do is stick this into a computer, right? And let me get to that in a second. But this is the overall idea, the model. Okay, we've got the end-of-life strategy coming in here at the left. We call those variables X. We've got a situational variable. These are the set of variables S coming into our model. Our model considers disassembly and shredding. Why disassemble before shredding? Because you want to get contaminant parts out so you can get a higher quality, both in terms of energy recovery and cost recovery for that product. You can go straight to landfill, right? There would be distances involved here. You can recycle the various end parts. All right, so it looks a little bit complicated, but it's only complicated in the model in terms of the bookkeeping. I mean, this is a linear model. At the end of the day, it's a huge model, but it's completely linear. Now, we use genetic algorithms to solve it, but you could break this down, right? You're talking about pretty simple modeling, zero-order modeling. So it becomes bookkeeping at the end of the day. So it's complicated, but not, I would say, hard. Just it's for the patient. Right? So you develop your model. You've got your end-of-life strategy coming in. You've got your situational variables coming in. And you get your environmental metric, in our case, energy recovery. as a function of X and S and the economic metric cost at the end of life in terms of X and S also. Okay, so that's our output. And these are our situational variables. You can't read them. Labor rates different. Transportation cost. Oh, no, I was incorrect. Per ton kilometer, the transportation cost was higher in Aachen than the U.S. We did look that one up. But they're almost the same. Well, but it might show up as being a little bit different. It turns out the transportation distances down here are vastly different. You've got much more transportation in Ann Arbor than you do in Aachen. The recycling infrastructure is in place over there, and it isn't in place here. For the math-minded, and I'm only aware of 3 or 4 of you in class anyway who are math-minded, but this is a multi-criteria optimization problem where we're trying to minimize the energy, say the environmental impact to generalize it, while we're maximizing profit. All right, so this is going to define our Pareto set. But we have to have a feasible disassembly sequence. We have to have a feasible end-of-life strategy, right? We're not going to recycle something that can't be recycled. We're not going to separate out from a shredder something that can't be separated out from a shredder. The regulations have to be met. In this case, the WEEE regulations in Aachen have to be met. Okay? And I'll ask one of your classmates to explain this if you're really interested, but I don't think most of you are. Okay? I'm saving time a little bit, too. But here's what it looks like when it all comes out at the end. And again, you can read more about it in environmental science technology. These are the Pareto sets. The triangles over here are straight to landfill. The diamonds over here are straight to a shredder. A shredder, remember, takes your product, shreds it up, gets the recycled fraction out, assumes recycles the recycled fraction, like the metals, at 100%, and then the other stuff gets landfill. So that's what we mean by shredding. This set over here means some disassembly is going to take place and some direct recycling. So we call this the DNR scenarios, disassembly and recycling scenarios. But there is a different degree of disassembly in each case, and they end in different places, right? So not only can the disassembly sequence change, but how long, how many steps in that disassembly can change. All the way down to the end here, and it turns out the end point is always the same, right? It costs the most to recover all the energy you can, complete and total disassembly and recovery, right? So we call that situation E, or result E here. Right, so that comes at the end. You get the most energy recovery. Energy recovery is on the x-axis. On the y-axis is profit. And you're looking at an Ann Arbor scenario where recovering energy, unfortunately, isn't very profitable. There are a few profitable energy recovery scenarios, but compared to just sending it to a shredder, they're not different in terms of uncertainty, if we throw uncertainty in here. Landfill, costs you a little bit of money, and you don't recover any of the energy, but to some degree it's easier, right? So shredding actually makes you a little bit of money, but it doesn't make you a whole lot of money. And what you're thinking about here, and one thing we have to really emphasize, I mean, you could talk about, oh, well, this says that in Ann Arbor you can profitably recycle a coffee maker, right? Well, can you really? I mean, the question is, it's not just about profit, it's about profit per time. Can you use the amount of time setting up this infrastructure is going to take you in a way that's going to make you more money? Right? What if it takes me 10 years to put that infrastructure together, and it's a real big hassle? Right? I could be out making other money. Right? The business folks in here know it's about making it's profit per time that you're trying to maximize, and not just net profitability. Right? So you might wonder why we don't see a recycling infrastructure here to the degree that we have in Aachen. Okay. By the way, I didn't mention that this case that I was pointing at doesn't even exist in Ann Arbor. This is Ann Arbor with a local disassembly infrastructure, right? A local facility where you can have this disassembly taking place, right? Here you are with your coffee maker. What are you going to do with it? You send it back to North Carolina where it was made and have them disassemble it? Well, we didn't know where to send it. So we said, well, we'll send it back to the manufacturer. They're in North Carolina. Here's the scenario down here, right? So this is your transportation really dominating here, right? And the costs involved with sending it back to North Carolina. In this scenario here, we assume, as there is in Aachen, local disassembly facilities that can handle that, right? And so you can see what a difference it makes if you have the local infrastructure, and we don't have that. Laws can help get that. We don't have it. WEEE exists in Europe, in Germany in particular, and they've got high landfill fees, higher than here in the U.S., much higher, almost order of magnitude higher. I didn't point that out. So, of course, that infrastructure is more likely to exist there. Okay. So here's the cost. This, by the way, is the line that defines the amount of cost you pay for electricity, energy that you buy from the grid. And basically what we're making an argument, the reason we put it here, is in theory, by some partial disassembly, you can make money relative to the grid, right? You can recover more energy from disassembling the part and recycling some fraction of it, right? So in theory, you can make money doing this, right? But of course, in practice, the distribution of wealth plays into it, right? The costs and benefits are not distributed in such a way where anybody could ever recover that, right? This isn't electrical energy. This is talking about preventing energy in a smelter somewhere down the road, right? So who gets that savings?
When you're talking about the energy savings, with the coffee maker, aren't a lot of those parts might be made elsewhere outside the U.S., so it doesn't even affect the U.S. grid?
No, the recycled material fraction goes into a waste stream that's U.S. So it's offsetting electricity here in the U.S. I'm not suggesting that the metal, the aluminum in the heating element is going to end up as aluminum in another heating element in Malaysia or Sweden or wherever the same could be made. It's a material fraction that's here used in the U.S. So it's offsetting the use of virgin aluminum here in the U.S. All right, so that distinction has to be made clear. All right, we're talking about recycled energy.
So one of those sets is for Aachen and the other one is for Ann
No,
Arbor?
this is the local disassembly network in the United States. This is the actual Ann Arbor, sending the coffee maker back to North Carolina, the manufacturer, and asking them to do it. And then they take the recycled stuff and then send it to New Jersey and Pennsylvania where the materials actually get recycled. Okay. Cost breakdown, all right, for total, so the situation E here, or I should say the strategy E, is total energy recovery. You got large labor costs and large transportation costs. In the profit, max profit, it's mostly labor. Okay. Now, before I compare to Aachen, and this is, you get a feel for how these things shake out. But this is looking at a sensitivity analysis on transportation cost. And now we're assuming local disassembly infrastructure here. Okay? Because that situation wasn't even relevant to look at. We say it's not profitable under that situation. Right? But if we had local disassembly, and it's not inconceivable to imagine that these things might happen in the relatively near future, having places that are set up to disassemble products, like Recycle Ann Arbor, but maybe it's more disassemble and remanufacture Ann Arbor. Right? Now, looking at that sort of situation, what we're talking about here is a baseline cost, and yeah, even I can't read it here. You'd have to blow it up on your slides. You basically can look at a case where there's no transportation cost and a situation where those costs increase per ton kilometer by 250%. Right? So you don't see really huge changes. Right? You end up with a strategy. Right? Now this is what we call P, is the max profit DNR strategy. So where there's some disassembly and recycling. Now, that strategy in the baseline case here is to recover the upper housing made of plastic and just shred the remainder. So it's one step. Right? So you can make a little bit of money. There's a good mass of plastic there. So you separate that out so it's not contaminated, and you can shred the rest. Now, if you increase the cost of transportation here, now it begins to make sense to recover the copper filter only and landfill the remainder. And this has to do with the infrastructure for recycling the plastic. Okay. So it just is the way it shakes out. Okay, so you can kind of see a discontinuous. This is where the strategy changes. You're looking at energy recovery on the left axis here and cost on the right axis. This line is the energy recovery. You can see it's flat, and then it jumps, changes. Okay. So I'm not really asking you to understand this, but just to get an idea that we can do this sort of situational analysis and look at these Pareto sets. And here in Ann Arbor, it's not very profitable to disassemble and recover the coffee maker at the end of its life. Okay. This is looking at labor costs, same idea. And you can see here it's very clear. As you have more labor involved toward total disassembly, and you increase the cost of labor, right, the slope increases, right? It's going to cost more and more to recover the energy. Here's a case where labor is free. Up here, if labor were free, it turns out that would be your cost-optimal thing to do, right? And you could think about using prison labor. There are people who've been talking about this. Free labor, and is that really free anyway, and is it ethical, et cetera? But if you had free labor, people doing this on a volunteer basis, well, that would be your profit best thing to do also. It's interesting that you can get energy and profit incentives to line up, right? If you had a case where people would work for free, or you can get incentives for people to do this as part of other jobs, right, that they're already doing, right? And that's a whole other issue. You get the idea. Okay, here's now looking at WEEE both in local Ann Arbor, that's up here, and in the Aachen case. The Aachen case is down here. Okay, so this is Aachen under WEEE. Now, it's restrictive. It means you have to recover, I believe it's about 65% of this coffee maker and recycle it. And you actually have to remove the LCD that's in there, and there's a little transformer in there. They have to take that out also, as required by the European Union Directive on Waste Electric and Electronic Equipment. Okay, so there's not too many things that you can do with it. So the Pareto set is quite small. Right? So there's a base case without WEEE, and then there's a case with WEEE. You see the costs are relatively high. So where's that money going to come from? Question. Right. This is looking at Ann Arbor under local disassembly and recycling. This is Ann Arbor under WEEE. Actually, I screwed this up. Sorry about that. This is Ann Arbor. I'm going to just erase what I just said. This is Ann Arbor under the base case, sending it to North Carolina. This is sending it to North Carolina under WEEE. Here, you've got local disassembly network, and then local disassembly network under WEEE. So actually, the WEEE reduces profitability, which is interesting. But you get some benefit. You're also removing toxics from the waste stream, right? So one could interpret this as being you're discouraging recycling, but at the same time you have to. If you had WEEE, you'd be over here. This is the Aachen case on the right. Sorry about that. Okay, under WEEE, it kind of looks like this one, so I got confused. But you see here that it's not profitable there either. Right. So comparing the situations, and now one can find the relative breakpoints. Right, one can analyze these curves and now try to represent it. Right, and I see the baffled looks. Right, but you can train yourself to read these. It takes time that's a little bit longer than we have. But here what you're looking at is the Ann Arbor. Here is the original case. The base case is number 1. Okay. Looks like local disassembly. Right. Case 2 is a 55% drop in the aluminum scrap value. So we put a 2 next to that. And if that happens, your max profit scenario changes. If you've got a 50% labor rate reduction, that's 3. So you look at curve 3. Right? So you can see that became flatter. 100% labor cost increase, as we saw. You can see that slope becomes bigger. Number 6 is WEEE. That's here. Okay, and then the little letters here, A, B, C, D, correspond to what you actually do under that scenario. So 6C, 6 means this is the WEEE scenario. C means the max profit design and, I'm sorry, C means the maximum profit disassembly and recovery or recycling scenario. It corresponds to letter C down here, which is performing disassembly steps 1, 4, 5, 8, and 9. You can go back to the liaison graph to get what that is, and then you shred the remainder. Okay. Now, could consumers really understand this? Well, the real environmentally minded people could, but probably not the everyday person would take the time to educate themselves on this. If you had an owner's manual with this at the back page, and you now had a place like Recover Ann Arbor, whatever we want to call it, doing this sort of thing, they could understand what to do with it. Because if you had that type of an operation in Aachen, Germany, or in Ann Arbor, United States, or in downtown Detroit, or in Lincoln, Nebraska, or Los Angeles, California, now you could basically go from here, use Ann Arbor as your reference, go into the numbers, and get a real good intuitive sense what you should do from a cost and energy recovery standpoint. Right? And get a very good sense straight away. You can do it for Aachen also. Right? So this is basically what we did. The details, of course, we glassed over like we so often do. Right? But again, trying to work our way towards providing this information. Designers can create this. The method wasn't so difficult. And if you were to read the paper, you'd see that with a little bit of investigation, a company could hire somebody, a consultant, to set up an infrastructure to do these types of labels within 6 months. It's not that hard to do once you know what to do. Of course, it depends on having life cycle assessment information available to you. That's why we picked a coffee maker. We really wanted to do a cell phone. And we didn't have good cell phone information when we started. Now we do. Will we go back and do this for the cell phone? It will still take some work. If we were paid to do it, we'd probably do it. But we're ready to move on in terms of intellectual development to other things now. So you get the idea. And I think with the conclusions here, basically, in general, we can say you can do this, right? And people should be doing this, coming up with explicit definitions of what the trade-offs are under different situations and bringing those out in the open. So you can't just claim ignorance and do nothing. If you're going to do nothing, at least the information's out there. Case study. From here, we saw that the localized processing in Ann Arbor is very important. And under localized disassembly, getting labor costs down is critical. Maximum energy recovery is always seen through complete disassembly and recycling. The max profit is very sensitive to situational variables, as you would imagine. Okay. And the strategies, it turns out that the end-of-life strategies are quite robust under WEEE. We saw that limitation on the Pareto front. So there aren't that many things you can do if the government's telling you do this. Right? So that was the basic sort of conclusion there. Are there any questions before we just spend a couple minutes wrapping up? Because I know you love guidelines, so that's why I just saved it to sort of blow through at the end. I mean, there's a lot of reasons to disassemble, right? And if there aren't any questions, right, well, we're basically talking about things you already know. We're trying to increase the use productivity of resources, right, which you can do in a number of ways, right? You can get a car that consumes less material by weight and burns less fuel, right? Cell phone housing that does the same, right? You can have more use per product. You can have 2 people using a car instead of 1 person using a car. Right? You can get rid of rare and harmful materials where you've got scarce resources. You try to substitute those for more plentiful resources. Or you can try to get things that are out there to last longer. Right? And that's really what recycling and remanufacturing is all about. Right? We talked about the fax machine. Right? Reusing to increase the service life of components of a fax machine. We had that example early on. We could talk about recycling, trying to get the material to last longer, right? Instead of just landfilling it and creating new material, right? So this is the basic tree and the reasons that we would have for disassembly. Design for disassembly, is a topic we don't really cover in this class because, again, I think only a few of you would really be interested in the details of it, but it's a fascinating subject. Generally, some guidelines here, if you can integrate parts together, especially parts that have compatible material, it makes a lot of sense. It makes sense to avoid mixing materials that aren't compatible. So if you got parts that may rattle, like a door, we looked at the design for disassembly of a car door for a Ford Focus. This was a project we did with Visteon. It was scary. Our senior design class was the first time that Visteon US had looked at design for disassembly and the end-of-life directive. That was about 2 years ago now in regulations coming out in Europe for end-of-life vehicles. Right? But foam was a big issue there. Right? So we could talk about stiffening issues rather than adding foam, because at the end of life, now if you can't mix the foam out because they were gluing it on, then it becomes quite difficult to separate it, and it's certainly costly to separate it, and you can't recycle the plastic that the door was made out of. I can't. You're conspicuously missing from 599 here has been that case study, because I'm under contract not to talk about it. But anyway, that was one of the things there in general. Don't mix materials. Foams makes a difference. Especially if you're going to be mechanically separating through a shredder. Manual separation, it turns out that if you follow the guidelines for design for assembly, you're probably going to have a design for disassembly that's pretty good. You can certainly cook up cases where that's not the case. But in general, follow the design for assembly guidelines. We'll go through some of those in just a second. Right? Wiring, it becomes important, right? Don't have tangling wires. Don't mix materials. Pretty intuitive stuff. Okay, so we kind of call this rule number 1 for design for disassembly. Follow design for assembly guidelines, right? But again, it's a guideline. So, don't follow design for disassembly or design for assembly guidelines blindly. People say, use snap fits all the time for design for disassembly. I go bananas when I hear that, and a couple of you know this very well. It turns out, look at a cell phone. Try to take your cell phone apart. Probably has a snap fit, right? A lot of them do anyway. And they're a real pain in the neck. If you don't have access to that third direction to kind of put that snap fit back in so you can pull it out, right? The removal direction is generally orthogonal or in a different direction at least from the snap fit direction. It can be impossible to do without destructive assembly. But it might be great for assembly but terrible for disassembly, right? Unless you have your snap fit that can disassemble itself. And there's research going on right now here in mechanical engineering on that topic, right? So don't follow these guidelines blindly, but they kind of make sense from a disassembly standpoint too, right? Minimizing the number of components, integrating components that are made of compatible material, minimizing the use of fasteners, right? You have to disassemble those too, and for disassembly they can rust and be even more difficult to take apart if we're talking about threaded fasteners. Don't require the base to be repositioned, right? The more effort one has to take to reposition something, the longer it's going to take. Maximize accessibility, that's obvious. Use straight line assembly and straight line disassembly, so you don't, again, have to reposition it. So you can basically kind of go down and try to minimize the number of tools you're using, right? The number of types of tools that you're using, right? When we were disassembling cell phones, we've done a lot of this in our group. Finding tools can be the hardest part, right? So make it so you can disassemble them with one simple tool. That's a general tool, standard tool. Let's see. Design for the use of retrievable materials, end-to-end symmetry, right? Like your car keys, right? As much symmetry as you can get, so it doesn't matter how you assemble it or how you disassemble it, right? So if you have an asymmetry in your assembly, make sure it's plainly obvious, right? So it's only, suppose your car keys only went in one way, but you couldn't really tell which way they were supposed to go, right? Then, it get really difficult to start your car, right? So make it obvious, like this way is up. Right? So there are guidelines out there, and it's not really our point here to do more than just make you aware of that there are guidelines out there, and there are some good. There's a handbook it's called the Mechanical Engineering Life Cycle Handbook. There are a lot of authors there. One of the authors was a former student of mine. in that book, there's a whole chapter on design for disassembly and some guidelines there. But I want to leave us with this issue of recycling and profitability in recycling. Right? When we're talking about end of life, whatever it is, we can talk about profitability, but we can talk about profit per time. That's definitely a take-home message from here. You can go use your time to make money doing other things, and you can't ignore that opportunity cost. So it's not just about profitability. Time is critical. And as societies become more developed, time becomes even more precious. Now, revenues, where do they come from? High-value components, of course. If it's gold, has a high value. Unchanged, undamaged product. If you're going to reuse something, obviously it's going to have a higher value than something that's either contaminated or damaged. You can recover energy, but you're not going to get much revenue from doing that. And these are some of the factors involved in cost. Right? If you're buying back product, if you are buying cell phones at the end of their life and reselling them, or remanufacturing, reselling them, that's a major cost that you have, as is the storage cost and your transportation cost, your labor cost, your equipment cost, your capital cost, the operating cost for your facility, right? And time. You can't forget time, the time you're investing per product. Right? All of these are common cost factors. And I'll end with an example. This is an example of a dashboard. It was done by one of my colleagues down at Georgia Tech. Bert Braz is his name, in the Systems Realization Lab down there. And basically, he was looking at the disassembly of a dashboard for a car. Basically, for this dashboard, to remove it from the car took about 35 minutes. And to get the relevant dashboard components out is another 35 minutes. So at $20 an hour, which is cheap, because you're probably not considering overhead there, we're talking just $23 just to get this thing disassembled to the degree it makes sense to disassemble it. Now, just those numbers alone, you'd have to recover more than 10 kilograms of pure copper and recycle it to break even, to get that cost back. There's not 10 kilograms in the dashboard. Okay. And in fact, there's only about 23 kilograms total in the car, for the car they were looking at. This was a 1990s vehicle. Okay. But basically here what you're looking at is the types of materials found in a vehicle, some of the major ones, their percentage in the car, mass percentage in the car, and the price for recycling for those materials that can be recovered. All right. Here, scrap price, sorry. And for some plastics. Okay. So the point is, it's not economically favorable or advantageous to recycle the components in the dashboard. Right. So the gauges would have to be resold for reuse, right? And the question is, who'd want it? Right? In fact, one of the reasons I got rid of a car of mine I had is I tried to fix the speedometer 4 or 5 times, and it never got fixed. I won't say who made it or what model it was, but it was always stuck at 55 miles an hour. And no, this isn't what I was just telling the police officer, and the only traffic ticket I ever got was in that car. But I knew darn well I was speeding. Anyway, long story. But the point is, that's where redesign really gets motivated. And one should use these types of analysis in the spirit of redesign. Right? And we haven't had a lot of design examples. Right? The best way to learn design is to actually do it. Right? So you can use what we've talked about in class, look at the various environmental dimensions on your product, look at recyclability, reuse, how feasible is it, where's your product ending up. You know how to do this now. And you can now look at your product and see what's feasible to do with it. Right? That's your job. Right? Hopefully we have had enough examples to at least inspire you to come up with these types of solutions in your own domains.